It's a great pleasure to have today Michael Buballa from Technical University of Darmstadt. As usual, I'm going to introduce a little bit our speaker. So he got his PhD in the University of Bonn. And after that, he has been 3 years in Stony Brook, where he was a postdoctoral researcher. And then he came back to Germany, where he did most of his career. And in 2004, he became a tenured senior researcher in Darmstadt, where he's now the leader of the nuclei, hadrons, and quark group. So it's not a surprise that he's an expert in QCD, and his research is in QCD. And a bit more specifically, he works in QCD phase transition, color superconductivity, baryon resonances, and things like that. And today's talk is going to be about phases of dense, strong interaction matter. Michael, the floor is yours.
Yeah, thank you very much for this nice introduction, and also thank you to the invitation. I already enjoyed nice discussions this week, and yeah, as announced, so I'm going to speak about phases of dense, strong interaction matter. And so to begin with, I would first explain what actually I mean by dense, strong interaction matter. And for this, let's have just a look at the scales here. Second. So I show here different scales here on more on the atomic level, so a crystal and an atom, and so those objects are, of course, governed by the electromagnetic interaction. And then if you zoom into this nucleus here, then we are 4 orders of magnitude smaller. So we have the atomic nucleus, and then the constituents of the nucleus, so the nucleons, protons, and neutrons, which are even 1 order of magnitude smaller. And then those consist of quarks, which up to now are considered to be point-like. Now, the essential thing is that, so this is now the realm of the strong interactions, which hold together the nucleus and also explain the interaction between the quarks and the nucleon. And so a rough estimate is just, if you go from the atom to the nucleus, the size shrinks by 4 orders of magnitude, and that means for the density, which is something like particles or mass per volume, we expect that the density should be at least 12 orders of magnitude larger. And in fact, if you look a bit more precisely, for instance, as an example, metallic iron has a mass density of 8 grams per cubic centimeters. And if you look at the iron nucleus, which has this radius, you come up with more than 10 to the 14 grams per cubic centimeter. So the density in the nucleus is even more than 10 to the 13 times larger than in the atom. Now, where do we find these densities in the universe? Actually, if we just look to the sun, the density is not very large, at least on the average. And even after the sun at some time will stop producing energy, it will shrink to a white dwarf, which is, okay, a million times denser, but still these numbers are small compared with these nuclei. But there are objects in the universe where we find these densities, and these are neutron stars. So this will not happen to our sun, but if we have a star which is 10 to 20 times larger than our sun, it might experience a supernova explosion and finally end up in a neutron star. And the neutron stars typically have masses of 1 to 2 times the solar mass, but a radius of only a bit more than 10 kilometers. And if you plug this in, then you find that in a neutron star, which could actually be considered as a macroscopic big nucleus, the density on the average is even twice that of nuclear matter density. And of course, this higher density is because the nucleus, this macroscopic nucleus, is just squeezed by the gravitation. Now, of course, if this is on the average, it means that in the center, the densities are even higher than that. And the question is how high, so how large is the density there? And we don't know exactly yet, but it could be something like 5 times nuclear matter density it depends on the equation of state. So if the equation of state is softer, it can be squeezed more, but then also the star becomes sooner unstable against the collapse into a black hole. So something like this is expected. Now, there are even situations where you can encounter, at least for a short time, higher densities in the universe, and this is when neutron stars collide. So there are neutron star mergers. Less than 10 years ago, this has been even observed in gravitational waves and other, also on the electromagnetic. So in that case, it was found that two neutron stars collided and finally went into a black hole. But during this process, for a short time, there could be densities which are even higher than what is can be found in a stable neutron star. Okay, so this is, and the question we want to ask is basically, how does the matter look into this very dense, strong interaction matter? Now, in the case of neutron star mergers, actually, it is not only very dense, it also becomes hot. And so I also should say a few sentences about temperature, which will also play some role in this talk. So again, let's start with the sun. So the sun at the surface has a temperature of about 6,000 Kelvin. At the center, it's much hotter because there's where the fusion takes place, so it's 10 million Kelvin. And also the neutron stars, at their birth, they are very hot and then cool down quickly within the first minute. But then for a large while, they keep their temperature of about 1 million Kelvin. So this sounds hot, but actually it is a low temperature on a strong interaction scale. And to see this, we should better switch to so-called natural units. So that this is basically where we put these natural constants h bar and c equal to 1. And what is important here, also the Boltzmann constant k. And then we can express the temperature in terms of an energy scale. And the conversion factor is just that 1 electron volt is about 10,000 Kelvin. Or in this talk, I will mostly use mega electron volt, MeV, and this is then 10 to the 10 Kelvin. And now if we compare this to a typical strong interaction scale, which is given basically by the masses of the lightest particles. So again, in this natural units, masses can be expressed in terms of energies. And the lightest strongly interacting particle is the pion, which has a mass of 140 MeV. So this would then even go to 10 to the 12 Kelvin, and then we see again that these temperatures which are reached on the sun or in the neutron star, they are basically zero on a hadronic scale, so they are cold objects. But in the neutron star right at birth, the so-called proto-neutron star, and also in neutron star mergers, you can achieve temperatures of the order of 50 MeV, for instance. So this is then not small compared to that. Okay, now in this talk, I want to talk about phases in this extreme strong interaction matter. And for that, what we are after is something like a phase diagram. And of course, all of you know the phase diagram of water, for instance. Here is a function of pressure and temperature. And then we have solid, liquid, gas. Actually, there are many solid phases at high pressure, but never mind. Yeah, of course, you all know that. So one thing I would like to discuss with this phase diagram is the following. So the solid is a crystal, so it has a certain symmetry, which makes it different from the two other phases. But actually, the liquid and the gas, they are not so much different. They basically, symmetry-wise, they are the same. And the only thing which happens, so there's a phase boundary here, first order phase transition. If you go across the phase transition from the gas to the liquid, there's just a discontinuity, a jump in density. And if you now go along this line here, this jump becomes smaller and smaller, and eventually you meet a point where this jump becomes zero, so this is the so-called critical endpoint. And above this point, you can go around this from the liquid to the gas or back without crossing any phase boundary, and this is just called a smooth crossover there. And I'm just mentioning this because we are also expecting that there could be something similar in strong interaction matter. Okay, so the main question we want to discuss here, and I will not finally answer, is how does the phase diagram of dense and hot strong interaction matter look like? So here's the outline of my talk. I just gave the motivation. And so since I was told that in general this is a broad audience here, I thought I should first deliver a few QCD basics which might be important to understand the rest, and maybe the QCD experts, which are also here, may check their emails in the meantime. And after that, I will return to the QCD phase diagram and discuss various objects which we expect there. Okay, so QCD in a nutshell. I mean, what probably most of you know is that quantum electrodynamics, in quantum electrodynamics, you can describe the interaction of electrically charged particles by the exchange of photons. And quite similarly, in strong interactions, we describe the interaction of quarks by the exchange of gluons. And in that case, the quarks carry so-called color charges, which are conventionally just called red, green, and blue. And in addition, actually, they come also in different flavors, 6 different flavors, but in this talk, we only need the 3 lightest ones, so up and down, and the not quite as light strange quarks. Okay, and as I said, the interaction is mediated by this gluon exchange. I also have put a Lagrangian here, which looks pretty innocent. So for those of you who are familiar with quantum field theory, so there's a covariant derivative where basically these gluons are hidden. And the main difference between the quantum electrodynamics and quantum chronodynamics is that because of the non-abelian nature of these gluons, the gluons also carry color charges, as you can also see here. So basically, they can change the color of one quark, say here from green to blue, and then carry the color along. And because the gluons also carry color charges, they can interact with themselves, and that makes the theory much more rich, much more complicated, much more difficult, but also much more interesting than the quantum electrodynamics. And one important feature which we have here is this running of the QCD coupling. Actually, this also exists in QED, but it's just the opposite. So if we go to very small distances or in momentum space to very large momenta, then the coupling becomes relatively small. And therefore, in this regime, we can treat quantum chromodynamics perturbatively. And this is actually why we believe that it is indeed the true theory. On the other hand, if we go to large distances or small momenta, then the coupling becomes strong and perturbation theory breaks down. Actually, these curves here are based on perturbation theory, so at some point we cannot trust them any longer. And then we really need non-perturbative methods to describe them. But exactly this regime is the most interesting regime, of course, as usually. And there are interesting features in this regime. And I mentioned 2 of them here, which are the most important one. One is confinement, which just is the statement that we cannot, so quarks and gluons, even though we believe that they exist, cannot be measured as isolated particles in a detector, but they only exist as bound constituents in color-neutral objects, so-called hadrons. And the second important quantity, which will also play a role in this talk, is the so-called spontaneous breaking of chiral symmetry. Okay, what is chiral symmetry? So chirality from Greek means handedness, and actually it's not exactly the same, but very strongly related to helicity, which you may be more familiar with. So basically, whether the spin is parallel or anti-parallel to the momentum. And it turns out that if you look at this QCD Lagrangian, which I've shown to you in the beginning, if for a moment you forget about the mass terms, then actually the right-handed and the left-handed quarks decouple. So basically, they don't talk to each other. This is the so-called chiral limit. Now, there are these masses, but at least for the up and down quarks, they are relatively small on a QCD scale, which means that this chiral symmetry is still a good approximate symmetry. And for the strange quarks, this still holds to some extent. Now it turns out that, so this is then an approximate symmetry of the Lagrangian, but it turns out that the QCD vacuum does not obey the symmetry. So in the vacuum, the symmetry is spontaneously broken. And basically, the reason is that the vacuum contains some non-vanishing expectation value, Q bar Q, which is actually the order parameter of this broken symmetry, the so-called chiral condensate, and this is non-equal to 0. And this breaks the symmetry in the vacuum. Now, this may sound quite formal to some of you, but the interpretation is basically, that's the way you could think of them, that this is that in the vacuum the quarks carry some effective quark mass, which is much larger than the original one. And I told you that these ones are small, but the masses break this chiral symmetry, and you can imagine that in the QCD vacuum the quarks somehow have some higher effective mass. And this can also explain the following phenomena. So before I've shown somehow this sketch of a nucleon, so you know that, for instance, the proton in the quark model can be considered to consist just of two up quarks and one down quark. And then in this simple picture, you would then expect that each of them carries about 1/3 of the nucleon mass, which would be something like 300 or 400 MeV. However, if you perform high energy deep inelastic scattering on a proton, for instance, you get a much different picture. So you find many quarks and antiquarks and also gluons. But these quarks here carry only a small mass, but much smaller than this. And this can be now really seen as some effect of the spontaneous symmetry breaking. So here we are in the perturbative regime, but once we get to this low energy regime, then basically the quarks get this larger effective mass, which explains then the nucleon mass. And so this can also be explained in terms of diagrams in QCD. So basically you can say masses are energies, and energies are related to interactions and potentials. So you can start with some bare quark, which has only a small mass, but then this gets stressed by gluons, and the gluons by themselves again by quarks, and the quarks also by other gluons, and so on. And if you sum this up, you end up with something which has a larger mass. And okay, I forgot. So again, this order parameter, so this chiral condensate, which I mentioned before, you can just imagine to be something proportional to this effective constituent quark mass. Okay, with this now I would finally really like to turn to the QCD phase diagram and discuss basically something like this picture here. So, okay, first of all, what do we naively expect if we go take, say, nuclear matter and we compress it? So here I just draw a sketch of nuclear matter. So we have different protons and neutrons, and they all consist of quarks, but they are somehow well separated, and the quarks are confined in these nucleons. Now, if we compress them, and as a theorist I can just put them into a box and then somehow compress them, then at some point these nucleons overlap, and it's hard to tell which quark at some point, which quark belongs to which nucleon. And so this would then predict that at some point the overlap is so great that basically the nucleons lose their identity, and the quarks become deconfined in the sense that they now can freely, within this box, freely move from here to there. And if you heat the vacuum, we would expect something similar, just because when we heat it, we create thermally mesons, pions, and others. And so also everything becomes denser packed with quarks, and they overlap. And so we also expect that then finally there could be some deconfinement. And actually this was already an idea, right, 1 year after QCD was formulated by Cabibbo and Parisi, they have drawn this kind of phase diagram. Unfortunately, why is this lower part covered? Maybe I can just, I don't know. No, okay. We have to live with it. Probably it's not so important. Here we have a phase diagram. This is, nowadays you draw it the other way around, but here's temperature and here's density, and then they said, okay, at low temperature and density, you are in a confined state, and at high temperatures and densities, you are in a deconfined state. But already in this paper, they said the true phase diagram may actually be substantially be more complex, and this is, in fact, what we nowadays think. Okay, yeah, so what is the contemporary picture of the phase diagram? This is this poster, which I've shown many times already from the CBM experiment at the Plant Fair facility in Darmstadt. I called it an artist's view, but actually yesterday Theo Motta gave me a true artist's view, a phase diagram drawn by his stepfather, who is a professional in these things, and I will come back to this later. So for now, let's rather have a schematic view on this. So this is basically what was drawn on the previous ones. So here we have now a phase diagram, not as a function of temperature and density or pressure, but as a function of temperature and quark chemical potential or baryon chemical potential, doesn't matter here, which is related to the density. And then we have various phases which are indicated there. And here at low temperature and densities, we have the hadronic phase, where we expect that the quarks are confined in hadrons and chiral symmetry is broken. Now, if we go up to higher temperatures, then we have the quark-gluon plasma, where the quarks are deconfined and chiral symmetry is approximately restored. And the way I've drawn it here, and I will argue for it later, is that actually there's similar to what we had with the liquid and the gas before. There's a first order phase boundary here, which ends at some critical point. And there's a lot of speculation whether this point exists and whether this has some experimental signatures, and people are looking for that. Okay, so there could be a critical point. And finally, at high chemical potential and not so high temperatures, there is this so-called color superconductor. This is a phase where basically quarks form Cooper pairs, and I will discuss this in more details soon. Okay, so and then there are various extensions and variations, which maybe I don't need to discuss right now. Okay, how do we actually, so these are just ideas and sketches, how do we actually investigate that? Now, of course, I said before, so there's perturbation theory, which should be valid at very high temperatures and very high densities. However, these are temperatures and densities which are far outside of any application to, say, neutron stars or existing objects. Nevertheless, so these calculations in perturbation theory exist, and they play an important role in benchmarking other calculations, say model calculations and others at lower temperatures and densities, because eventually, of course, they should be consistent with these perturbative calculations. But otherwise, you have a question? Okay. This is simply, if you are at high densities, then because this is a system of fermions, then basically the Fermi momenta are very high, and therefore the momenta where the quarks scatter are determined by these scales, and therefore it is kind of perturbative. Okay, there are some caveats to that. So as I will say later on, at high densities we also expect these color superconducting phases, which is by itself a non-perturbative phenomenon, which nevertheless can be studied using some weak coupling expansion in a systematic way. So did this answer the question?
So you have many gluons, I guess. Okay, you said it just the energy
Yeah. I mean, yes. So I'm myself not a person doing these calculations, but they exist, and I think this is what plays the role. I mean, it's also that the gluons, okay, in principle, the gluons, they could, of course, if you just have some emission of collinear gluons, then their momenta can be small. But basically, most of the quarks have high momenta, and therefore, if they scatter, then it's more likely that the gluons also have the momentum exchanges. Actually, it's of course so the momenta of the gluons determine whether it's perturbative or not. So in the end, the gluons are of course essential. Okay. Yeah, and then we have so basically for most what we want to do here, we have to use non-perturbative methods, and the most well-known and is lattice QCD, where people basically compute the QCD partition function, so which is a path integral on a discretized Euclidean space-time lattice using Monte Carlo methods. And this is actually probably the most reliable non-perturbative approach, also very systematic. And the only problem is that these Monte Carlo methods do not work at non-vanishing chemical potential. Therefore, there we are restricted basically to mu equals 0 or the surrounding of that. Now, there are also other non-perturbative methods based on QCD, which are functional methods, and I mentioned two of them here. The two most important Dyson-Schwinger equations. So we have shown, I've shown already these diagrams here, which is actually a Dyson-Schwinger equation, and the functional renormalization group, which I don't plan to explain here. So these methods are in principle exact, but they need to be truncated. So what does that mean? So for instance, if you look at this Dyson-Schwinger equation here, so this is an equation for the inverse quark propagator, and on the right-hand side, you also have this inverse quark propagator, so this is some kind of self-consistency equation, which makes it non-perturbatively, that's good. But as an input, you also need, for instance, this, so this is dressed by a gluon, and you also then need the properties of the gluon and the quark-gluon vertex. For those, you also have Dyson-Schwinger equations, but they need, again, higher inputs. And in principle, this is now a set of infinitely many coupled equations. So in principle, it's exact, but in practice, it's not doable like this. So you have, at some point, you have to cut the system, and this is called a truncation. And this makes the uncertainty, because somehow it is maybe not so easily controlled. But in principle, it's based on QCD as well. And in some regions at mu equal to 0, it can be also compared with the lattice, for instance, and it does quite well there nowadays. Okay, and finally, then there are QCD-inspired models. These are models. This is not QCD. And therefore, they have less predictive power. They have model parameters, but they are very often well-suited for explorative studies. And actually, one of the models, which is something I have worked a lot with, is the Nambu-Yuna-Lasinio model, which is a model where you don't have gluons, but just a point interaction between the quarks. And the main feature of this model is that it also, so the interaction is chirally symmetric, and you can have the spontaneous chiral symmetry breaking, in that case, by summing up or solving this kind of diagrams. And in fact, when the model was invented in 1961, QCD and even quarks were not yet known. So at that time, this were interpreted as nucleons, but nowadays you take it as a quark model. And then there are many extensions of that, in particular to non-zero temperature and chemical potential, which we also will use here. Okay, now let me just show some results here. So let me begin with the case mu equal to 0, and there we can, of course, as I said, use the lattice. And what is shown here is our lattice results for basically, this is something like the chiral order parameter, Q bar Q, scaled by the value at t equals 0 as a function of temperature. And then you see, okay, if you increase the temperature, eventually this order parameter becomes very small, but it does so continuously and it does not really go to 0. So this is not a true phase transition, this is just a crossover. So we now believe that the phase transition along the q equal to 0, so the t-axis basically is just a crossover, as I've drawn already in the previous diagram. Now, how does it look like at finite, non-zero chemical potential? So, as I said before, there is a so-called sign problem. So, lattice QCD does not really work. But already in 1989, this case has been studied within the Nambu-Yuna-Lasinho model by Asakawa and Yazaki. So this is just a model calculation. And this is the phase diagram they got. Actually, case 1 and case 2 are just two different parameter sets. So it's either this or that, or something in between. So this shows already what I said before. So there's no clear prediction by it, but it can give you ideas. And this was actually very influential. So unlike what we nowadays do, they had the temperature here and the chemical potential there. And these dashed lines here are just the crossovers which we had before. So if you go along the t-axis, then there is this chiral crossover. But if you then go to low temperatures and high chemical potential, then there is here something which is a solid line, and that was a first-order phase transition. So what they found in the model is that there is a first-order phase transition if you go along the mu axis, and then just as we've seen in our phase diagram of water with the liquid gas, there is a critical endpoint where the first order ends, and then there is just a crossover. So this is just a model. But in the meantime, there are calculations based on the functional renormalization group and also Dyson-Schwinger, and they also find indications for a critical endpoint, and they even agree with each other to some 10% level, and they predict that there could be a critical endpoint at a baryon chemical potential of about 600 MeV and temperature 120 MeV. So then there should be a first order phase transition or something like that here, but they couldn't really reliably calculate in that region yet. Okay, so with this, now let me go to my next section, which is discussing this region of high baryon density and not so high temperatures where we expect that there should be color superconductivity. So what is actually color superconductivity? Of course, all of you know what is a superconductor. So if we just have a metal and cool it very low temperatures, then eventually the electric currents, there are electric currents with no resistance. And there are many types of different superconductors, and I'm not a condensed matter person, but there are complicated things. But the simplest and first and most well-known theory for the origin of this is the BCS theory, and basically they explain the existence of an energy gap which leads to this non-resistant behavior by the condensation of so-called electron Cooper pairs. So there are pairs of electrons which cause that. And in full analogy, now in strong interactions, we could also have Cooper pairs of quarks. And because the quarks carry color, we call this then a color superconductor. Okay, so why should we actually expect, or why does this happen at all? To this, let's go back one step and first look at a system of non-interacting fermions at t equals 0. Then basically, because we have fermions, so we fill up the levels up to some Fermi momentum, and then the energy level is then at Fermi energy, which at t equals 0, in that case, is just equal to the chemical potential. And the excitations which we have, then there are particle-hole pairs which you can excite from this. Now, what we are usually doing is we apply the grand canonical formalism treatment, and in order to determine the ground state of such a system in terms of temperature and chemical potential, we have to minimize the free energy of the system. The free energy, I just remind you, is basically the internal energy, which I call here E total, minus some temperature times entropy, minus chemical potential times the number of particles. Now here we are at T equals 0, so the second term doesn't exist. And basically if we then just add one additional particle, then the change of the free energy is just E minus mu. So we can also add a hole, which means removing a particle below the Fermi surface. So because of the removing, there's a minus sign here, and because we are below the Fermi surface, this thing was in parentheses is negative, so basically it's just the modulus E minus mu, so both of them can be written in that way. And now the important observation is, I mean, it looks trivial, but exactly at the Fermi surface, where E minus mu is 0, basically we can simply add particles or holes without having any free energy cost. The free energy for adding these particles or holes is just 0. Okay, and that actually leads to some instability if we add a little attraction. So here is again, I didn't write it, but this is now the momentum, and this is again this free energy, so E minus mu, and this is what we would have for the non-interacting particles. Now if we add some arbitrary small interaction, and so I just said here, it doesn't cost any energy to add particles or holes, but now if we have even an attraction, it would even further lower the energy. So for the system, it would be beneficial to create more and more particles and holes, and then they just condense there. And this leads to some instability. And basically, this leads to a rearrangement of the whole Fermi surface in such a way that eventually it doesn't look like the blue curve, but like the red curve, where there is some gap which prevents now this from becoming further unstable, because now it does cost some free energy to create further quasi-particles. Okay, now there's, from these arguments, there follows one thing, namely that this Cooper pairing is actually an effect which happens at the Fermi surface of a system. And the other thing is that usually, and this is what these BCS pairs are usually, what they usually look like, is that these are pairs of particles or holes with with a vanishing total momentum. So the two particles which are paired should just have opposite momenta. So they should have opposite momenta and both be on their Fermi surface. Now in the following we will see that we very often have the situation that we have to pair different species of particles. And then it is not necessarily that they have the same Fermi momentum. And then this simple mechanism does not always work. So it only works if the Fermi momenta of the two particle species are about the same. Okay, now let's have a somewhat closer look to this. So in QCD, we have an attractive quark-quark interaction, which then should lead to this Cooper instability. By the way, in that sense, color superconductivity is more natural than the ordinary superconductivity, because in the metal you have electrons, which first have, I mean, they both have negative charge and are repelling each other. And then you really need some phonon interaction in order to explain where the attraction comes from. The quarks do have attractive channels. I mean, after all, they form hadrons, so there should be attractive channels. And then they form these Cooper pairs, which are related to some expectation so-called diquark condensates. And before I just wrote QQ, but to be more precisely, so we have two quark fields here, and then some operator in between which determines the quantum numbers of these pairs, and there you actually have many possibilities. So for the quark, for the electrons, you basically have the spin of the two electrons, but for the quarks, we also have color and we also have flavor degrees of freedom. And the only so this gives you many possibilities how to pair them, and the only strict restriction is the Pauli principle, which tells you that in the end, this operator should be totally antisymmetric. Now, one can find arguments that the most attractive channel is actually a spin zero channel, so the spin part is antisymmetric. It is also in color space and a color anti-triplet, which is also antisymmetric, and then following from this, then the flavor part must be also antisymmetric. And antisymmetric means you cannot pair the same species, flavor species of particles. So basically, we always have to deal with the pairing between different flavors. So here's some examples. So the spin part is antisymmetric, the spin 0. This color anti-triplet is also antisymmetric. And therefore, we can, for instance, pair up and down quarks also that the wave function is antisymmetric. So this is an isospin 0 combination in this case. Okay, now this was just with up and down, but we also have the strange quark, and then we can, by this, form a lot of possible combinations. And just by going through them, basically one possibility is, of course, there is no pairing. This I will call normal quark matter. Then we can have the situation that, for instance, there's a pairing between the up and the down quarks, but the strange quark might be too heavy and does not participate. This is known as the two-flavor superconducting phase, the 2SC phase. Then there could also be cases like this, which I think I will not discuss here, but then there's the situation that all the up, down, and strange quarks somehow are involved in the pairing, and this phase is also quite well known as the color flavor locked phase. Now, color flavor locked simply means if we also show the color structure, then this has a certain symmetry which makes this kind of pairing, because you have 3 flavors and 3 colors, so you are able to do that, which makes this form of pairing very symmetric, and it has very nice properties somehow. No, I mean, okay. There are papers where also charm quarks are considered. So the point is that somehow what people who discuss this have in mind are basically neutron stars, and there the charm quarks don't play a role. They still sometimes, people still sometimes then consider the case of very large or infinitely large chemical potentials in order to apply these weak coupling calculations I was mentioning before, but they still neglect the charm quarks because they hope to learn something about the situation in a neutron star. Well, this is not clear. I mean, okay, let's say compact. Okay, I should better say compact star. So I'm anyway talking about a situation where we might have a quark, a core of the neutron star or of the compact star or hybrid star, which where we have deconfined quarks which can form these things. That's right. Yeah. Okay. So the question is, which of these phases is favored? And for this, I should come back to this picture I had before, where I just pointed out, basically, in order to have the pairing of the different flavors, we should have approximately the same Fermi momentum. And now the strange quark mass is already a bit larger than up and down quark masses, or quite a bit. And therefore, the Fermi momenta of strange and say the up-down sector is different, so the Fermi momenta are given from the chemical potential, and basically then the masses enter in this way. And then it somehow depends on how large is this chemical potential compared to these masses. Yeah. No, exactly. I will exactly come to this. So basically what you can say is if the chemical potential is really much larger than even the strange quark constituent mass, or the constituent mass at that density, then basically the Fermi momenta are similar. And then because of this higher symmetry, we expect that there is a CFL phase, whereas if the chemical potential is of the order of the strange quark mass, or even lower, then the strange quarks could not participate in the pairing, and we have a 2SC phase. And now this is covered. I don't know why this happened, actually. But anyway, so you still can see, basically, this was some paper, educated guess by Raja Gopal, more than 25 years ago. So at intermediate mu, you have a 2SC phase, and at higher, you could have a CFL phase. And a few years later, we did some NGL model calculation where we basically confirmed that. But actually, this contained really some aspect referring to your question, namely in this NGL model, as I explained before, we can also calculate the dynamical masses, and they come out density and chemical potential dependent. And basically now the calculation of the masses and the gaps is done on some equal footing. And so here these are the gaps. So the blue curve is where we only have the up and down pairing, and the red one is where the strains are involved. So here we have a 2SC phase, and then there's a first order phase transition to the CFL phase. Here on the left, I show the corresponding constituent masses, which are first large, and then there's here for the up-down, there's a basically the chiral phase transition, but the strange quark masses, they still stay large for a while and then become only lower. So just this comparison, whether mu is bigger or smaller than the strange quark mass, by itself is not sufficient because the strange quark mass also depends on mu, and so therefore somehow this can stabilize the 2SC phase by itself. Now there's some additional turn, and this is when you really go to compact stars, there are constraints, and namely that matter in a compact star is in beta equilibrium, and it should be electrically and color neutral. Now beta equilibrium basically means, so you know the weak decay of the neutron, so a neutron goes to a proton, electron and antineutrino, or in the quark level it's a down quark goes to an up quark. Or similarly, you also have that for the strange quark, and then now in matter, everything should be in equilibrium, so you have back and forth processes, so you can have processes like those here. And chemical equilibrium then just means that the sum of the chemical potentials on all sides of these processes, so the rates should be the same, and that boils down that the sum of the chemical potentials should always be the same. And that relates then the chemical potentials of the species. Now in a cold neutron star, because the weak interactions are very weak, the neutrino basically can just escape, and therefore its chemical potential is 0. And then one finds that the chemical potential of the up quark plus the electron should be equal to that of the down quark and equal to that of the strange quark. So this I put here again, this relation. In addition, we have electric neutrality. So basically the sum of the charge densities should be equal to 0. So the up quarks have a charge of 2/3 of the elementary charge. The down and strange have -1, and the electron -1/3, and the electron has -1. So this sum should be equal to 0. And then there's something like color neutrality. Okay, in reality, it should be a color singlet. It's a bit more complicated. So that should also be fulfilled. But the last has actually a minor effect. Now, for the others, what we find is that we can rewrite the first relation like this, that the electron chemical potential is just the difference of the down and up chemical potential. And from this, we conclude that the electron charge, which is basically the cube proportional to the cubes of that, the electron density is much less than the up and down densities. And that means that basically this electric neutrality should be more or less fulfilled by the quarks by themselves. So we just have here this relation. Now, if we are in the CFL phase where we basically have up, down, and strange quarks to an equal amount, so then we have 2/3 -1/3 -1/3, so this is automatically fulfilled. However, as I said before, the strange quark is more heavy, therefore we expect to have less strange quarks to begin with, and this has to be compensated by to have more down quarks in order to get 0, and that means that now, in fact, all the flavors have different Fermi momenta, so even the pairing between up and down is not clear whether this happens. And okay, this is again now a result of an old NGL model calculation. So this is the phase diagram I've shown you before without these neutrality constraints. So here we have the 2SC and the CFL. Now, if we switch on these neutrality constraints, it looks, first of all, much more complicated. And so then here, actually, the up and down pairing was no longer possible. So we have a normal quark matter phase. Here we still have a CFL phase. 2SC exists still at high temperatures. And then there are a lot of phases where there's a little g meaning standing for gapless. And this is something which was discussed a lot 20 years ago. So these are so-called gapless superconducting phases which come out of such a calculation, but they were shown to be actually, or there were indications that they are actually unstable. So in these calculations, one can also calculate the Meissner masses of a gluon. So for a superconductor, you have something like a Meissner effect, which can be interpreted that the photon gets a mass, and the same you can do for the gluons. And in these gapless phases at low temperatures, these Meissner masses came out imaginary, and this is an indication that something is unstable. And that was a long discussion what that actually means. Now, there was another issue. So this is, as I said, an NGL model. So it's a model that it depends on some coupling constants. If we just increase the quark-quark coupling by a bit, we find a rather differently looking phase diagram. So here we have 2SC, CFL, so it looks much more than before. So also we have a strong parameter dependence. Yeah, so these are the two issues we had there, and this basically tells you that probably we are stuck with the models. And so one way now one should go is, in order to reduce the parameter dependencies, actually we should really start from QCD, and that was done already like 10 years ago, in also a calculation I was involved with. So this was a Dyson-Schwinger QCD calculation, but I told you before that there we have to put some truncations, and at that time this was not that far developed, and we found that also with these calculations the results were strongly dependent on the truncation. So what I just flash here are different results for these phase diagrams. So at that time, this was not yet really fully developed. In the meantime, there was a lot of progress in non-color superconducting Dyson-Schwinger equations, and we are just planning a project, or we are just starting a project where we want to redo these calculations with the now state-of-the-art truncations, and hope that maybe we find some more solid results. There are also some results in the functional renormalization group more recently, and they find very large gaps actually there, which was also surprising to me, and we will see how in the end this will compare to each other. Now there are also some ways just to use empirical information from neutron stars and heavy ion collisions and neutron star mergers in order to constrain these parameters. And okay, but I don't want to comment on that. Now, yeah. So the other thing is, as I said before, so this was one of the phase diagrams I've shown, and there were these unstable gapless phases, and the question was, what does that actually mean? And so my favorite explanation is that this actually means, so far in this phase diagram, we have assumed that these color superconducting order parameters are really constant in space. So we just have homogeneous phases. But in fact, what we could have is also crystalline phases where they vary. And there are arguments that this could indeed happen. So this is, again, a sketch of the situation. We have two species which we want to pair with two rather different Fermi momenta, so the green and the red. And basically, what could happen if we want to pair them? So if we still use this BCS-like homogeneous pairing, then we first should equalize the Fermi momenta. So somehow we have to reshuffle the quarks that they have approximately equal Fermi momenta, but this costs free energy. This is something the quarks wouldn't do by themselves. Then, however, we can pair, and then we gain free energy, and it depends on whether we lose or gain more, whether this is possible or not. And then there was some limit already in ordinary superconductors with magnetic fields that basically the pairing is still possible if the difference in the Fermi momentum is less than the pairing gap divided by square root of 2. Now, an alternative, however, is that you say, you just keep the quarks, you keep the Fermi surfaces as they are, and you pair them nevertheless. Then the pair doesn't have zero total momentum, but it has a finite momentum, and in coordinate space, this means that there is some, it corresponds to some wave number, so to some oscillations. This is usually disfavored by kinetic energy and also by phase space, but of course in cases where this does not happen, it could still happen. And this has been described in the 60s by Fulde and Farrell and by Larkin and Ovchinnikov in the case of ordinary metallic superconductors, and therefore usually in the community these phases are called Loft phases. Okay, and there are arguments that these chromomagnetic instabilities are indeed instabilities to walk towards these Loft phases. And some time ago we have actually studied whether they exist. So basically what is shown here is now the free energy gain as a function of the difference in the chemical potential of the species. And the free energy gain with respect to no pairing at all. So this zero line means no pairing at all. This solid line here is just the ordinary BCS pairing, and then basically you would find up until here the pairing is allowed, and then there's a first order phase transition and it's not allowed. And with these kind of Loft phases, I mean, then there are different forms of them. We find a window where other people also found that where this is possible. So these phases might indeed exist. What is still missing is a systematic survey of the phase diagram of that. Okay. Yeah. In principle, what is now missing is still my last section, which is not very long, but looking at the clock, I don't know how much time I do still have. So
a bit up to you. Let's say.
Oh, okay. Then I will try just. Actually, I provided already the main arguments. So I just was talking about crystalline color superconductors, and now I go back to our chiral phase transition, the one which we had here, and I will argue that there could even also be kind of inhomogeneous crystalline phases there. And so why should that be? So the analogy is in color superconductivity, where we had quark-quark pairing, then they are favored for equal Fermi momenta, and they are somehow stressed by the unequal densities. And then these inhomogeneous phases, which I just was talking about, they are some kind of a trade-off. So there's some spatially varying condensate, and so these extra quarks, which we have because of the unequal Fermi momenta, they are basically sitting in the regions where the condensate is zero, and the condensate is large, where there are basically no extra quarks. So this is somehow the mechanism. Now for the chiral condensate, this can be considered as a quark anti-quark pairing. So it was QQ bar, or Q bar Q, the condensate. And they are favored for vanishing Fermi momenta, and they are basically stressed by non-zero densities. So basically we have let's say a quark sitting here and an anti-quark sitting there, and the larger the Fermi momentum is, the more they are apart, and the pairing becomes less and less favored. And again, here we can have the trade-off that we have spatially varying condensates, and the quarks are just sitting in the region of low QQ bar. And indeed, it was found again in an NGL model, for instance, by Nickel, that these phases could exist. So this is a phase diagram as we did it before, so allowing only for homogeneous phases. Here, chemical potential and temperature. The blue line is a first order phase transition. Here we had this critical endpoint. Now this was a calculation in the chiral limit, so then there will be a second order phase transition here, and this is a so-called tri-critical point. Now if he allows for these inhomogeneous phases in some way, he found that there's this orange region, and in this orange region, within that model, the inhomogeneous phase was favored. And the striking thing was that basically this inhomogeneous phase completely covered the first order phase boundary. So it could be really an interesting thing. Now the calculation of all this is, of course, not really trivial, because basically, I mean, what we always do in order to get these phase diagrams is we minimize the free energy now with respect to the condensate. So before this was just masses and these pairing gaps, but these were just numbers. So it's a minimization of a function with respect to some numbers. Now, if we say the condensates are somehow inhomogeneous, so they are functions by themselves, then this is the minimization of a functional which depends on these functions m, and the shape is not known, and therefore this is a priori very difficult. And so this is therefore even in field calculations and unsolved problems, and there are just different strategies. One is you just use restricted Ansätze for this modulation, and then you minimize with a finite number of parameters. Basically, this is what was done in this nickel calculations, which I've shown you before. The second method is a stability analysis. So basically, you start from the restored phase and then investigate the stability of the homogeneous ground state with respect to small inhomogeneous fluctuations. And for that, at least in these models, you don't need to make an ansatz for the shape. Both has been done. Okay, and by looking at the time, I think I will not, unfortunately, discuss now further details of that. I just want to say that, and that's also one reason why I'm here. So what I've shown you so far for these inhomogeneous phases was built based on model calculations, and together with Theo, we have worked out some strategy how we could also investigate that with Dyson-Schwinger equations in QCD. And so just last year, we had some, say, proof of principle of that idea where we used a simple truncation, but still, but already in Dyson-Schwinger QCD, but with a simple truncation. And there we found indeed some indication of a region where these inhomogeneous phases exist. Of course, this was a simple truncation, and the idea now is not this week, but within the next years, again, to go to more realistic truncations and see what comes out. So, okay, then I'm indeed almost at the end, and as a conclusion, I just want to leave this nice phase diagram drawn by Theo's stepfather, where you find this nice critical endpoint here, and many features, also experiments, which they're fishing in the sea and looking for further surprises, what could be there. Okay, thank you very much.
Thanks a lot. Time for more questions, even about the talk or about the last plot.
So I have a very naive question, which is, in the last 20 years, for example, can you say some of the, what has been learned about the core? So obviously there are all these different models, but is there something you can pin down and say, okay, we understand this that we didn't understand 10 or 15 years ago?
Okay. I mean, it's a difficult task, and things are moving forward slowly. So the real pin downs have been made at mu equal to 0 in lattice QCD. So there we really learned that there is no phase transition, but just a crossover. And also going away a bit from that. There are, I mean, concerning this critical endpoint, which is something people are indeed looking for about 25 years or longer, both experimentally and theoretically, this has not yet been pinned down really, but maybe further constrained. So I remember that, so I always said that in lattice QCD, you can only perform calculations at mu equal to 0. This is not exactly true, because you can do some kind of extrapolations, Taylor expansions, calculations at imaginary chemical potential, which can be then extrapolated into the region. And 20 years ago, there were still some predictions of the critical endpoint in a region where it is now already excluded. So they are pushing it away further. And on the other hand, I mean, which I just mentioned, is that these functional methods, so the Dyson-Schwinger and functional randomization group results, they somehow converged on a region where this critical endpoint is to be expected. Now the question is, can this further be confirmed by something else? This is not yet done, and in fact, I'm also a member of a big consortium working exactly on QCD at extreme conditions, and we just applied and are optimistic that we got it for 4 more years to do this research, and we will see.
More?
Regarding these neutron stars, right? So what do we actually know about the density that it can be reached? Is it 5 times, 10 times?
Yeah, okay.
Because if you look at the graphs there for superconductivity and all, this is much, much higher.
Yeah. So, and maybe this is partially also an answer to the previous question. So 20 years ago, if you looked into some papers, they said, okay, it can be up to 10 times nuclear density. Now, as I said before, the densities which can be reached depend on the equation of state. So the softer the equation of state, the higher the densities can be reached. But if the equation of state, also the softer they are, the lower are the maximum masses of neutron stars which can be reached before. And these are now constrained by observations. So, so 20 years ago, people only knew about neutron stars up to 1.4 solar masses, but now we know cases of at least 2 solar masses, which somehow has reduced, I would say, this upper limit from 10 to more like 5. Now then, we had the gravitational wave observations, which give some information about the tidal deformability. So when the stars come closer to each other, they get tidally deformed, and you can learn something about that, which is also a measure of softness. And it turned out if you take, I mean, of course, at low densities, you really have chiral effective theories and good nuclear theory and all that. If you just continue those calculations, they are in conflict with the tidal deformability. So there are some arguments that this could hint to that we need some extra softening at higher densities somehow. So it should be stiff at low densities and then some extra softening at higher densities. And some people argue this shows there must be some kind of a phase transition. Up to now, you can only take these various models and see which densities you can reach. And I just checked because we also recently did one calculation. And in our case, it goes basically up to about 5 times nuclear matter density. Usually, you reach the 2SC phase. In some cases, also CFL. So I mean, this is still not completely clear.
Hey. About these neutron stars also have magnetic field. Some neutron stars have magnetic field, rotation, and other effects. Do you know the effects of these on the?
So, the magnetic fields, of course, they do have an effect. The point is, again, one should compare that to the scales of nuclear interactions or of strong interactions. So people are studying also. I mean, this is also something which can be done and has been done on the lattice. What are the effects of magnetic fields on the equation of state and so on? And there usually you need magnetic fields which are much higher. I mean, there are magnetars which have a pretty high magnetic fields, but still, if you express these magnetic fields in terms of pion masses, they are much lower. And if they are as high as as the pion masses, then actually the neutron star, they would really have an impact on the energy density, the energy momentum tensor. The stars would look weird, like a torus or something like that. So I would say the magnetic fields you have in a neutron stars do not strongly affect these things. The rotation, of course, the faster the rotation, the more stable the star is. But on the other hand, also, then maybe the density is not affected so much. I don't know what.
So maybe a provocative question, also
Sure.
my ignorance. So the non-Lagrangian model is a model. So it depends on the parameters, as you said. It's also non-normalizable. So maybe it depends also on some cutoff that you have to put. So my provocative question is whether this model can be falsifiable from experiments.
Okay. Yes. It depends on what you call this model. So, I've been using models quite a lot, but I've always been very critical about that. So I don't feel too much provoked by this. So indeed, there are these parameters, and as I've shown you, basically, I would not trust any quantitative prediction unless there's some model-independent statement, but that you know anyway. Then, so I mean, there are of course model equations of state which have been calculated before these two solar mass stars have been detected, and now you can say, okay, no, this must be wrong. Then the question is, I mean, this is semantics, whether you say the model is wrong or just these parameters are wrong. So I really like these models to see as something which, because they are simpler than true QCD, they can you give hints on what could happen and what is worthwhile to study more deeply. But in the end, they cannot predict anything.
Some more? Yes.
So, first of all, thanks for the lecture. It was very good.
Oh, thank you.
So there are a lot of cool phenomena involving QCD. And when you say like color superconductivity, I tried in my mind like visualize a pairing between this and the common superconductivity, where you have like, for example, the coupling of electrons and phonons in the crystals. So in this color superconductivity, is there like a mind picture to see this phenomena, or is this like so out of this world to think that you just agree to the results?
So, well, what you just mentioned, so I was expecting actually when you when you started your question that you are asking whether there's also something like currents without resistivity, and for that, of course, you would need something like a color current, which is, I mean, this exists, but it's hard to imagine. And anyway, I mean, what I was not talking about at all was that, of course, QCD, like also QED, is a gauge theory, and basically all these simple pictures rely on basically we fix some gauge and look at that. So there are many phenomena which are similar. So as I first said, there is this kind of pairing which creates a gap in the spectrum. So at least if you imagine we are at some high density where the quarks are deconfined, and so they could form something like a Fermi gas, and they don't, because there is this pairing. So this is very similar. There's also, I mentioned this briefly, something like a Meissner effect. So this is this phenomenon that in ordinary superconductors, magnetic fields cannot penetrate. Okay, there are even first order and second order, or superconductors of first and second kind. All this has also been calculated or investigated for color superconductors. It's just this thing with not having any resistance. This is something I don't know any analogy. By the way, I mean the quarks, of course, do not only carry color charges but also electric charges. So the question is, are these color superconductors also electric superconductors at the same time? I mean, if you have this pairing. And so there are some interesting things, namely it turns out that in some cases, even though you would naively think so, they are not, because you can find some combination of charges which then still where these superconductors are still neutral, or the color superconductors are neutral under some so-called Q tilde charge, which is a linear combination of the true electric charge and or the 8th gluon, something like that. And but in principle, then the question again is also in a neutron star. There was the question about magnetic fields. So do they influence the magnetic fields and things like that?
Thanks.
Actually, just a curiosity. What about the critical chemical potential? Does it depends on the combination of these superconductivity?
So the critical chemical potential for what exactly?
Because there is a transition, right? When you increase this chemical potential, at some point you get.
So okay, we have several critical chemical potentials which I discussed. So for instance, like first for the chiral phase transition, then later between different color superconductors, and again in more or less they depend on the masses and the sizes of the gap of this these particles. Yeah.
Some more? Okay. If not, we can thank our speaker again.
Thank you.